Well, now you can also
Okay. All right, so to recap what we were talking about on Wednesday, one of the big issues with, excuse me, low carbon energy is the need for what we call critical minerals. And we've talked about where those critical minerals come from. I kind of dunked on cobalt a bunch on Wednesday. We'll probably come back to that at some point. The other one that I want to highlight is lithium. So lithium is greatly needed. Let me go back to where is that plot that I had? It's in here somewhere. Oh yeah, here it is. Okay, so lithium is this light green one here, and it's extremely important for electric vehicles because it's used in the batteries. And as more and more renewable energy, specifically wind and solar, get integrated into the electric grid, we will need more and more energy storage to make up for the fact that those sources of energy are inherently intermittent, right? So the sun doesn't always shine, the wind doesn't always blow. And so if you want to store those, lithium ion batteries are a very good way of doing that because they have the right kind of discharge cycle, right? They'll discharge over hours, like when you need it on a hot day in the late afternoon, that sort of thing. So anyway, we need a lot of lithium. There's probably going to be a growing need for it. Most of the lithium that is used right now comes from Australia, Chile, and China. And the way that they extract it is lithium can form a salt, lithium chloride, which is highly soluble in water. And if you're in the right part of the world, you can find these high salinity brines that contain a significant amount of lithium in them. This is just a little side note here. In my previous life as a well log analyst, I remember doing some analysis on some wells that Dow Chemical had drilled in Arkansas, and they were, basically very, very poor oil producers. I think they produced upwards of 99% water cut. So 99% of the fluids coming out was water. But so you're probably asking yourself, what was Dow Chemical doing drilling oil wells in Arkansas? And the reason was that in that particular part of Arkansas, in the formation they drilled through, the brine was very high in bromine. And so they were stripping out bromine from the water. Some of y'all probably noticed, actually, this would be a good news item, so I don't want to steal anyone's thunder, but ExxonMobil over the summer, I think it was, or maybe it was last spring, announced that they are getting into lithium extraction from brine. And this is an emerging area. The reason is that, as we see here, currently the way that we produce lithium is to pump the water out of the ground and just let it evaporate, okay? Now, that's not a terribly great way of doing it because, for one thing, you're losing all that water. It's just evaporating. So, a ton of lithium takes about 500,000 gallons of water to make. That's a lot of water. The other issue is that the way ExxonMobil is proposing to do it is that they're going to use produced water from oil and gas wells, which contains not just lithium, but a lot of other stuff. And you've got to deal with that other stuff as well. And so what they're actually looking at doing is using some kind of a membrane extraction. So like I said, this is an emerging technology area, and hopefully we will see that come to fruition sometime in the future, because obviously the demand for lithium is going to continue to grow. Another little side note is that about a year ago, or a little more than a year ago, the price of lithium just kept climbing and climbing and climbing. And a lot of people started thinking, wait a minute, do we actually have enough lithium on the planet to meet our needs for sustainable energy? And a lot of people started looking at it. And then actually the answer is yes, we have way more lithium than we need. And so the price of lithium is actually going down right now. And that's interesting because this way of producing lithium is cheap, right? All you need to do is pump the water out and wait. Membrane separation is expensive. Okay, membranes typically need a high pressure differential across them. Creating that high pressure differential requires energy. Manufacturing the membranes requires energy. You have to wonder about what the economics of those projects are. And thinking about what ExxonMobil is proposing to do, you might worry that maybe they might just scrap it if it's not going to end up being profitable, because right now lithium is quite cheap. So anyway, where was I going with all that? Oh yeah, this is how most of the lithium in the world is produced right now, is just by evaporation. Okay, now the other issue is that right now in the United States, we do not have a good domestic supply of lithium. And I think, as we saw from the commodity price shocks that occurred after Russia invaded Ukraine, the domestic consumers here in the US, and for that matter in every country around the world, are susceptible to disruptions in the global supply chain. And so that was part of the rationale behind some of the components in the CHIPS Act and the Inflation Reduction Act to try to jumpstart the creation of a domestic supply chain for a lot of these critical minerals, one of which is lithium. And so now you've got companies that are proposing to start doing this sort of thing in the US, or maybe using leaching to get lithium out. And so here's an example. This is an article in the New York Times from a couple of years ago talking about one particular company, Lithium Americas, that were proposing. Actually, I should go back and see where this mine is in the permitting process, if they're actually going forward with it. But they were proposing to have an open pit mine in Nevada. And they did a feature on it. And here's this guy, this rancher, and he's like, what's this going to do? The water table is going to drop by about 12 feet. I need that water for my cattle. What's going to happen with all the tailings and the waste that's going to come out of this mine is that, they're using sulfuric acid, there are radioactive elements mixed up in there. What's all that going to happen? So, this gets back to the whole thing about, yeah, your electric car is great, but it comes with all these other issues that you need to think about and that need to be solved. Okay. I don't want you to think that all the stuff I'm talking about this week is like, oh yeah, energy is terrible, we should not use any energy, blah. Okay, that's not the point. These are all solvable problems that good engineers are needed to fix. And I hope you all take that to heart. Okay, this was an interesting article that I came across the other day, so I added a couple of slides in here. There's an additional kind of climate change aspect to these evaporation ponds for lithium extraction. So over 60% of global lithium comes from two regions in the world. One of them is called the Lithium Crescent, which is in the Andes, a little bit in Bolivia, mostly in Chile. And the other one is from the Kadam Basin, which is in northern Tibet. And these are both very high elevation, very arid regions. And they're already water stressed, okay, and you're pumping a lot of the water out. But there was an interesting article here looking at what's going on with changes in the water cycle in these two areas as a result of climate change. So what we've got here, we have time series going back to 1960 for annual precipitation, potential evapotranspiration. That's basically how much water could evaporate into the air, okay? Vapor pressure, which is a measure of humidity, and then average air temperature. And so the red lines here correspond to the Kadam Basin, and the blue lines are the Lithium Crescent. And so you can see they've got trends that they fit to these time series. The ones that have asterisks are the ones that are actually statistically significant. So, so for example, precipitation over this time period decreased a little bit in the Lithium Crescent, but it's not by a statistically significant amount, okay? So when you look at how all these things are changing, you can see what the different effects are going to be in these two regions. And so in the Lithium Crescent, less precipitation could fall in the future, and that would mean more water stress to an already water-stressed region. In the China example, actually, they're seeing more precipitation and more of these extreme flood events that are happening. So, that's a bad thing. If you're trying to evaporate your lithium and a flood comes along, then, that's all going to get washed away. Not only are you going to lose your lithium, then all the stuff that was mixed up in the lithium, those evaporation ponds, is just going to flow downstream and end up somewhere where you probably don't want it. Let's see, if you look at evapotranspiration, very few effects in the lithium crescent, no change, but more evaporation in the Kaidam Basin, which will increase water stress. In both cases, we're seeing increases in humidity and air humidity. And this, again, if you have more precipitable water, you have more chances of having extreme rain events. The other thing is that both regions are becoming warmer. And what this means is that these are both areas that are high elevation and cold. And it's a similar issue to what was going on in California prior to this past winter, which is that they rely on water storage in snowpack, okay? And so if you start not having precipitation fall as snow, but fall instead of rain, you're going to disrupt the entire hydrologic cycle in that region. So again, there's, this whole thing is all wrapped up together about, lithium extraction and climate, the water cycle, and all this stuff. So it doesn't operate in a vacuum, I think is the point here. Okay, so anyway, to sum it up here, critical minerals mining has its own issues that need to be addressed moving forward. Okay, so if I go back to this quote that I showed you on Monday about, if it ain't broke, don't fix it, to, just keep increasing prosperity in people's life expectancy and that sort of thing. It does seem like that the way we're doing it right now could use some improvements. So let's think about what that is. All right. I have gone nearly the whole week without actually defining what sustainable energy was, and nobody noticed. All right. So now we're going to define what it is. There's two good definitions that I found. There's a lot of very lousy definitions too, but these are the good ones. So this one from the group at MIT, it's a little wordy, but harmony between the equitable availability of energy-intensive goods and services, preservation of the earth for future generations. Okay, you kind of get the idea there. Brundtland, 1987, that's probably everybody's favorite definition because it's more pithy, right? Meets the needs of the present without compromising the ability of future generations to meet their own needs. That is sustainable energy. And I think the key thing between these is that we are meeting people's needs. We're meeting them where they are, giving them the energy that they need, and also thinking about future generations' ability to do that. So we don't want to do it in a way that's going to mess things up down the road. Okay. Now, one thing I want to touch on here is, and for you to be aware of, because this is driving a lot of kind of international policy around sustainability and sustainable development, is the United Nations Sustainable Development Goals, or they're often referred to as the SDGs. You'll probably come across these, and there's 17 of them, and they're all very, very good goals to have in mind. Obviously, there's, climate action is there, affordable and clean energy is there. But the thing with these is that if you create a truly sustainable energy ecosystem, then you actually can address all 17 of these goals in various ways. So there's the IPECA, which stands for the Global Oil and Gas Industry Association for Environmental and Social Issues. Don't ask me how the acronym is related to that, but that's what it is. They had a very nice publication. It's, I guess, 7 years old at this point, mapping the oil and gas industry to the Sustainable Development Goals. Okay, and what they did was they said, okay, so what are the issues? And they're kind of picking on oil and gas here because they are the Global Oil and Gas Industry Association, right? But the issues they highlight here are general to all forms of energy production. Okay, so we can use more sustainable energy to provide access to energy to people who currently don't have enough of it, and that will help with poverty reduction, for example. Another one is if your energy is truly sustainable, then you will be looking out for human rights and government corruption and that sort of thing, and that helps with SDG 16. So there's a lot of these follow-on effects that are very beneficial from making sure that our energy is truly sustainable. So, it's not just about not putting CO2 into the atmosphere or not having child labor mining cobalt, okay? It's about all of this stuff wrapped together. It's a much bigger issue than we're certainly going to tackle in this class, because we're only looking at the engineering aspect of it here. And so how can we make energy more sustainable? Well, there's really two main ways of doing it. Okay, you can generate and use less of it. Now, there's actually, this is, increased efficiency actually is a real thing. That at least in the United States and Western Europe, we are certainly using less energy per capita now than we were 20 years ago. And the reason for that is because a lot of the things we use now are more energy efficient, okay? For a good example of this is LED light bulbs use a tremendously smaller amount of energy than incandescent lights. So, things like that we just, take for granted in our daily lives. When I think about the cars that my parents drove around when I was, a little kid, they got 8 miles to the gallon, and you wouldn't be able to find a car like that anymore. So it's just stuff like that. But here's the deal: if you're looking at this, there come to be some ethical issues in telling countries that are not, that are still developing that, well, we were able to enjoy all this great stuff because we used a whole bunch of energy. You guys aren't allowed to do that. Okay, we're just going to come around and tell you not to do that. That's probably not the right way we want to do it. Okay, really, the other way to do it is to generate your energy and use it in better ways. And that's really what we're going to focus on in this class. So generating energy from what I'm calling low waste sources, waste being kind of a catch-all term for emissions, particulate matter, that sort of thing. And then existing energy sources, you need to reduce the waste that's associated with those as well. So, not only integrating more renewable energy into the electric grid, but also decarbonizing natural gas power generation through implementation of CCUS and that sort of thing. It all has to happen together. And because this is an engineering class, we're going to focus on what are the engineering challenges and the engineering solutions to doing it. Okay. The end. Any questions about any of this stuff?
Are they established inside of the UN or?
No, so yeah, the IPECA is not, they're a separate non-governmental organization. But yeah, they, I think they work closely with some of those UN groups, but they're a separate entity. Okay. Cool. All right, what's up next? Okay, so we're going to get even more fundamental here. I've gone almost the entire week without telling you guys what energy is. Did that occur to you? It occurred to me. Okay, so we're going to do a little bit of thermodynamics today, which I'm sure you're all really stoked about, because I know I am. Okay, so energy, strictly defined, okay, is the capacity for doing work or transferring heat. We'll talk about what work and heat are in a little bit. We know that any object or a system of objects has a total energy, which is given by Einstein's equation here, okay? So the total energy of a system is some very, very large number, right? Because you take the speed of light squared, so this is like 300 million meters per second, you square that, and you've got, trillions and trillions of joules basically locked up in energy. So we typically don't talk about total energy because the numbers are very large. We talk about changes in energy, and we call that delta E. So that's what we're going to be thinking about today. Okay, so I told you I would define heat and work. Heat is energy transfer through contact with something with a different temperature. Okay, so temperature is a measure of the amount of thermal energy, and you can transfer that, right? And so that's what heat is. It is a energy transfer. Work is basically everything else that's not heat. Okay, so when we think about other types of energy transfer, so you can think about potential energy, kinetic energy, chemical energy. So anything that changes those types of energy, that's going to be work. So basically anything except heat. And then enthalpy is the total heat content, and then entropy is the amount of disorder in the system. And we'll come to that in a minute. Okay. There are two laws of thermodynamics. Most of you probably know these. The first is conservation of energy. Okay. You conserve energy in any process involving the exchange of heat and work between a system and its surroundings. So you kind of have to define what the system is and what the surroundings are. But once you've defined that, the energy has to be conserved between those two things. The second law is often referred to as the arrow of time, but what this means is that if you combine the entropy of a system and its surroundings, that total entropy is always going to increase. Okay, so you can reduce the entropy of a system, but that has to come at the expense of increasing the entropy of its surroundings, because you've always got to be increasing entropy. Okay, so we're going to illustrate some of these quantities with a very simple experiment. So let's imagine we have a piston and it's filled with gas. I don't know what the gas is, but it's pink. Now let's compress that gas. We're going to apply a force to the shaft. We'll call that force F. And so we know that during this process, we have to conserve energy. We have to obey the first law of thermodynamics, or else the thermodynamics police are going to come arrest us and put us in thermodynamics jail. So delta E, that's the change in the energy. That has to be the sum of heat transferred and work done. Okay. And the way we define this is that, let's see, Q is the heat transferred to the system from its surroundings. So that's positive Q. And then work done on the systems by its surrounding is positive W. Okay, so whenever you're doing something to the system, that's positive. Whenever the system is doing something to its surroundings, that's going to be a negative number. We'll come to that in a minute. Okay, now, there are different types of energy that this gas can have. Okay, there's internal energy, and that just has to do with the chemical composition, the atomic bonds, that sort of thing. And then there's kinetic and potential energy. So kinetic is how fast it's moving, and potential is where it's located relative to some field, gravity, magnetic, something like that. Okay, and you can change all these things. Internal energy can be changed with temperature, but a bunch of other things involving, phase, chemical reaction, that sort of thing. Kinetic, obviously, you'd change the velocity, and potentially you'd change its location. So you can put it from the tabletop to the floor, and that changes the gravitational potential energy. Okay, now we are doing work on this gas here and changing its energy. So there's two different types of work that we're going to consider. One of them is what's called pressure volume work. And this, it's a kind of funny way to think about it. You think about compressing the gas, you're changing the pressure and the volume of it. But really, the way we define pressure volume work, it's how much work the system does, basically moving everything else out of the way to make room for itself, okay? When you're just sitting here, okay, you are displacing air. So you're doing work displacing that air, even though you might not feel like it, but you're doing work. The way we express this, it's actually an integral of the pressure as a function of volume between two different volumes. That's how we define PV work. And we'll come back to this in a minute. There's a path dependence on how you do this. The other type of work is shaft work, and that's anything that's not PV work. So these are things like electricity doing some work, mechanical works, things like that. So those are the two different types of work we're doing. Okay, and so we can break out the energy term here. So this is this total change in energy is going to be the sum of the changes in the three different types of energy, right? Internal, potential, and kinetic. And then that's going to be equal to the heat transfer plus the two different types of work. And the one thing you'll notice here is that the PV work takes a negative sign. And you're probably wondering why that is. Well, remember, when we were defining work earlier, I said positive numbers are what are done to the system. The way we've defined PV work, the system is doing that to its surroundings, right? It's kind of doing the mime thing. And it's going to be negative. Okay, so that's what we have. So for our system here, we need to take this expression here. This is general. And let's formulate the first law of thermodynamics. So the first law of thermodynamics is that energy has to be conserved. Okay, so that means that we start with this expression. Now, for simplicity, let's assume it's isothermal, and that means the temperature doesn't change. And so that means that the internal energy isn't going to change either. So delta U goes away. Let's also imagine that the system is not moving. It's at rest, so the kinetic energy doesn't change. And so the only thing that's changing is the potential energy. So the change of potential energy has to be given by this expression over here. Okay, now we can insert some different terms over here, okay? And we will say that we're doing PV work on this gas because we're changing the volume and changing the pressure. And so we can re-express this to give what's the shaft work that's going to be required to compress this gas. So there's going to be a change in the potential energy. There's going to be the PV work that we do, and then there's going to be the heat transferred between the gas and its surroundings. So that's the question here, is if we're conserving energy, what's the shaft work? And that's how we get it. Okay, so that's the simplest way of doing that. And again, this is for an isothermal system, so no temperature change. Okay, there's an additional way that we can define this. We can also define it in terms of enthalpy. So remember, enthalpy is the total heat content of the system. And so it's equal to the internal energy plus the pressure volume work that's being done on the system. And so we can re-express our change in energy in terms of enthalpy change. And that's going to be equal to this term over here. So again, for our isothermal process that we just came up with, we can express the shaft work in terms of change in enthalpy rather than PV work, and then the potential energy change, and then the heat transfer. So that's just a different way of thinking about it. Okay, we'll come back to this gas here in a minute, but the next thing I want to talk about is entropy. So remember that entropy is how disordered the system is. And this is an important concept because, so we had that very nice news item at the beginning of class on carbon capture. And the amount of energy required to separate CO2 from air actually has to do with entropy. So we will come back to this in our unit on CCUS. But first we have to come up with some definitions here. So let's imagine that we have a system that can attain a certain amount of different configurations. We're going to call that capital omega. Now, what do I mean by different amount of configurations? Okay, so I see you all out there sitting in chairs, okay? You are all in particular chairs. But you could conceive of you all sitting in different chairs within the room. And so the amount of different combinations where everybody could be potentially sitting with respect to each other is going to be this capital omega for where you're sitting. Okay, so it's the number of different ways that you can put the system together. When you think about gases, it is the number of different ways that they can mix with each other and where the atoms actually are. So as you can imagine, omega is usually some very large number because, even just for, 62 people sitting in a classroom, that's already, I think it's basically 62 factorial is how many different configurations there are. So, which is a big number. Okay, so, but the other thing is that if you think about it, the more possible configurations there are, the more disorder in the system there is, right? So if there's only one way that I can all put you together to sit in your chairs, that means it's a very ordered system. And so that would have very low entropy. So we'll say that entropy, it's going to be some function of the number of different combinations that are out there. And Boltzmann figured out what that function is, but I'm going to walk you through the reasoning here. Okay, so let's consider now two different systems. They have two different entropies, and they have two different possible configurations. Okay, so maybe it's you guys sitting in your seats here, and then the people sitting in the seats in the classroom next door. Two different entropies, two different possible configuration numbers. So if we consider the combination of those two classrooms, that's going to have a different entropy, and it's going to have a different number of possible configurations, right? Because if you're just sitting in here, you're not worried about where you're sitting relative to somebody in the next room. But if we combine those, then you have to be. Okay? Now, what that means is if we consider the total possible configurations now in the two systems, well, we know just from basic probability, that's going to be the product of the two different possible combinations, because we've got 62 factorial combinations in here, and they've got probably 30 factorial or something over there. Well, then the total number of configurations, if you're considering where everybody is there relative to where you are here, it's going to be those two multiplied together, right? And so that means that the entropy of that combined system is a function of the combined number of total configurations, which is, we can just substitute that product in there, okay? Now, one property of entropy is that it's additive. So the entropy of the two systems is just going to be the sum of the individual entropies. And I'm not going to go through the proof of that, but that was one thing that Boltzmann worked out. And so that means that if S1 plus 2 is equal to this function of the product of the omegas, that means that this function here is equal to the sum of the functions of its individual components. And the only function that satisfies this is the logarithm function, okay? Right, because the logarithm of the product of a number is simply the sum of the logarithms of those two numbers. And so Boltzmann figured this out and came up with this expression here, where he said, okay, the entropy is just going to be the natural log of the number of configurations multiplied by some number, which now we call Boltzmann's constant, and it has this value here. One thing you'll notice about the units of Boltzmann's constant is that it's energy per unit temperature, okay? So that implies that there's a temperature component to this, which makes sense. If I increase the temperature, I'm going to increase the amount of disorder because the molecules are all going to be moving around. Okay, and so the second law of thermodynamics says that a change in the energy of a system can only happen if the total entropy, so between the system and its surroundings, that total entropy, it has to increase. So if I do something where, okay, let me see how much you understood about entropy. Which has more entropy, pure CO2 or atmospheric air? Who thinks pure CO2 has more entropy? Who thinks that has less entropy? Good. That's absolutely right. Because if the more number of different molecules you have, the more number of different ways you can put them together. So air inherently has a higher entropy than CO2. If I want to remove CO2 from the air, I'm going to decrease the entropy. The only way I can do that is by increasing the entropy of something else, okay? And that requires an energy input. And as we'll see, particularly for removing CO2 from ambient air, that energy that's required is considerable. There's a very big thermodynamic penalty associated with that. You know that the concentration of CO2 in the air on average is roughly the same as the amount of caffeine that's in coffee, about 420 parts per million. That's an interesting factoid. Okay, now overall entropy can only increase with time, and the entropy of the universe is gradually increasing with time. This is why that second law of thermodynamics is sometimes called the arrow of time. And this is an interesting thing. So there's this concept in astrophysics called heat death, which is basically eventually, as the universe expands, it's going to lose all its energy, and there's basically going to be no energy. Everything is going to be completely homogenized. We'll reach a state of maximum entropy. And this is an interesting thing to think about. If you reach a state of maximum entropy and entropy no longer changes, there will be no sense of time moving forward or backward. You won't be able to tell. Okay? So think about that. Or don't think about that. It'll keep you up at night. Okay. How much of this do I want to get into today? You know what? I'll leave this for next week because this is all this path-dependent stuff. Okay, that's all for today. I hope you all have a fantastic long weekend. Don't come Monday. I won't be here.